Hi class, this is part 2 of the blood vessels lecture. So there are 3 different ways that things can cross the walls of the capillary. Okay, so in diffusion, this is where smaller things can just cross via simple diffusion, right? Just passing through. Okay, so this would be like oxygen, carbon dioxide, glucose, amino acids, which make up proteins, and some smaller hormones can cross via simple diffusion. Transcytosis, this is how larger molecules that are lipid insoluble, so this would be like insulin, this is how these can cross the capillary walls. So they cross in vesicles. Okay, so they need to be carried in this vesicle in order to cross the capillary wall. Bulk flow, this is another passive process similar to diffusion, which is also a passive process. So this is where a large number of things like ions, molecules, or things found in fluids can move together in the same direction across the capillary. So this would happen from an area of higher pressure to an area of lower pressure. Okay, and as long as that pressure difference exists, it's going to keep occurring. Okay, so this is more important for regulating the volumes of blood versus interstitial fluid. Okay, right? If you have too much pressure in the interstitial fluid, it's going to push back into the capillary, and then vice versa, right? Too much pressure in the capillary, it's going to push out into the fluid surrounding the capillary. So filtration, this is a movement of fluid in solutes driven by a pressure gradient from blood capillaries into the interstitial fluid. So you can think of it being filtered out from blood into interstitial fluid. Okay. So these are the 2 different types of pressures that promote filtration. We'll talk about this in more detail. Reabsorption, this is the opposite. So movement from the interstitial fluid back into the blood capillary. Okay, and these are the 2 pressures that promote reabsorption. Okay, so what are all these pressures? Hydrostatic pressure, this pushes things out of the capillaries, and how high or low the hydrostatic pressure is depends on the systolic blood pressure. Osmotic pressure, this is pressure from that protein albumin. So this is the pressure that albumin is exerting. And albumin helps to keep water in the bloodstream. Okay, so this is about 25 to 26 millimeters mercury. Hydrostatic pressure, this is of the interstitial fluid. So it should be 0, but if it was higher, it would push fluid into the capillaries. But in a normal, healthy person, it's 0. Okay, so it really doesn't affect anything. And then osmotic pressure of the interstitial fluid, this is about 1 millimeter mercury. So very, very low pressure. So water always follows solutes, right? Like sodium, for example. So it pulls substances out of the capillaries because that water in the capillaries, or the fluid in the capillaries, is going to follow solutes out. Okay, so this looks kind of complicated. We're going to break it down, okay, and try to make it a bit simpler, okay? So our net filtration pressure, and remember, this is the pressure pushing out from the capillary. This will be our blood hydrostatic pressure plus our interstitial fluid hydrostatic pressure, which again should be this one here should be about 1 millimeter mercury. Okay. Then we need to subtract our net reabsorption. Okay. This would be our blood colloid osmotic pressure, which is about 26 millimeters mercury pushing into the capillary, plus our interstitial fluid hydrostatic pressure, which is also flowing into the capillary, okay? So we want our things flowing out minus what's flowing in, and that gives our net filtration pressure, okay? So we have 31, our BHP is 31, and our interstitial fluid osmotic pressure is 1. So these are both flowing out. So we're going to add those together, 35 plus 1, so we get 36, minus our blood colloid osmotic pressure, so 26, plus our 0 here, interstitial fluid hydrostatic pressure. Okay, so 36 minus 26, we get about 10 millimeters mercury is our net filtration. So this here that we just went through is promoting filtration at the arterial end, right? So filtration is leaving the capillary, and then promoting reabsorption, right? So we want to filter at the arterial end, right? Because we want our red blood cells to be pushed out to bring oxygen and nutrients to our tissues. At the venous end, we want reabsorption because we want to take any waste back into the venous system to be brought to the heart and then lungs to be expelled. So this here would be our blood hydrostatic pressure pushing out of 16 millimeters mercury, okay, plus our interstitial fluid osmotic pressure pressing out of 1 millimeter mercury, so 17, minus our blood colloid osmotic pressure pushing in of 26, plus our interstitial fluid osmotic pressure pushing in to the venous end of 0. Okay, so 17 minus 26, we get about negative 9 millimeters mercury is the net reabsorption at the venous end. Okay, and then blood flows from the capillary into the venule, okay, because of this pressure. Okay, so let's just go through this general picture as well. So we have lymphatic fluid coming from our lymphatic capillary. We're going to go through the lymphatic system and immune system in the next chapter. Okay, so we have this kind of filters through our interstitial fluid and helps to clean it out. Okay, this returns to our blood plasma into the arterial and then into the capillary. Then we have a net filtration pressure of 10 millimeters mercury pushing our blood out, okay, and nutrients and things out. And then we move through. Now we have our oxygen poor blood here because of net reabsorption at the venous end. Okay, so now we're getting our carbon dioxide and any wastes being pushed back into the capillary, and then it flows into the venule, then the vein, then to the heart, then to the lungs. Okay, so this is known as Starling's law of the capillaries. Okay, so this states that under normal conditions, okay, a healthy person, the volume of the fluid and solutes that is reabsorbed is almost as large as the volume that is filtered. Okay, so different things that affect blood flow. So this is how much blood flows through a tissue in a given time period. So this is in milliliters per minute. Okay, so the total blood flow is the cardiac output. Okay, so this is the volume of blood that circulates through either the systemic or the pulmonary blood vessels every minute. Okay, so cardiac output is our heart rate times our stroke volume. We already talked about this when we went through the heart as well. Okay. So contraction of our ventricles in the heart, this is what generates our blood pressure. Okay, so blood pressure is determined by our cardiac output, our blood volume, right? If we don't have enough blood volume, say we're bleeding out, then our blood pressure, of course, would decrease, right? And our vascular resistance. Okay, so how dilated or constricted our vessels are, basically. Okay. Higher the blood pressure, of course, the greater the flow of blood. So remember, our high pressure system is in the arteries, right? So from the aorta, that's where we have that high pressure being pumped from the left ventricle into the aorta. Okay, and in the arteries and arterioles, we still have this high pressure. Okay, in the arterioles, it does start to decline. Those are connected to the capillaries, and then by the time we get to our veins and vena cava, our pressure is very, very low, right? We need a lot of help from like the skeletal muscle, for example, right, to push our blood back up to the heart because that pressure system is so low in the veins here. Vascular resistance. This is the opposition to blood flow due to the friction between blood and the walls of the blood vessel. Okay, so the higher the vascular resistance, the smaller the blood flow, right? The more you kind of fight against the blood flow, the smaller the blood flow is going to be. So this vascular resistance depends on how big the blood vessel's lumen is, the viscosity of blood, so that means how thick the blood is. Okay, so if you're dehydrated, your blood's going to be a lot thicker, more viscous. Or if you're very hydrated, it's going to be less viscous, more liquid. And total blood vessel length as well. Okay, we already talked about this, so I'm going to skip this. So here are all the factors that affect our blood pressure. So these are all things that increase venous return, right? Increase blood volume, our skeletal muscle pump, respiratory pump, and vasoconstriction, which we talked about in part 1. Okay. This would increase our stroke volume, as well as if we had increased sympathetic impulses or hormones from the adrenal medulla, like our adrenaline, right? This would increase stroke volume as well and increase our cardiac output. Things can also increase our heart rate, like those sympathetic impulses can also increase our heart rate. Or if we have increased sympathetic impulse or decreased parasympathetic impulses, these would both increase our heart rate and therefore increase our cardiac output, increasing our mean arterial pressure. Okay, so this would increase our blood pressure. If we also had an increased number of red blood cells, like if we're polycythemic, this would increase our blood viscosity, right? Make it thicker. Okay, and then this would increase our vascular resistance, our systemic vascular resistance. Okay. If we had an increase in total blood vessel length, this would also increase our systemic vascular resistance. Or if we had a decreased blood vessel radius, so vasoconstriction, right, constriction of the blood vessels, this would increase vascular resistance, increasing our mean arterial pressure. Okay, so these are all things that would increase our blood pressure. Okay, remember in our medulla oblongata, that is where we control our heart rate. Okay, it also regulates contractility of the heart and diameter of blood vessels. Okay, so these would all affect our blood pressure and therefore our blood flow. Okay, so we have input to our cardiovascular center. This can be from our other brain centers, from proprioceptors, which monitor movement, baroreceptors, which monitor blood pressure, and chemoreceptors, which monitor blood acidity. Okay. Based on those inputs to our cardiovascular center in the medulla, we can send out impulses to effectors. Okay. Through vagus nerves, which is part of the parasympathetic system, which would decrease our heart rate. We could send out information through our sympathetic nerves, which would cause vasoconstriction. Okay, this would increase our blood pressure. Or to our cardiac accelerator nerves, which are also part of the sympathetic system, which would increase our heart rate and contractility. Okay, baroreceptors, these are those pressure receptors, like a barometer measures pressure in the air. Okay, so these baroreceptors are important neurons, and they monitor the stretching of the blood vessel walls and of the atria as well. Okay, so you don't need to know too much about that, but I just wanted to mention how in general how that works. Okay. So this is showing a negative feedback loop for blood pressure. Okay. So we have something that decreases our blood pressure, like maybe where we have a large bleed or something like that, right? This would cause the baroreceptors in the aorta, right, to be activated. So there would be less stretch. So this would decrease the rate of nerve impulses. This would alert the cardiovascular center in the medulla and the adrenal medulla to increase our sympathetic and decrease our parasympathetic stimulation to increase our heart rate. The adrenal medulla would secrete epinephrine and norepinephrine, which would cause constriction of the blood vessels. Okay, and this would increase our systemic vascular resistance. Both of these things would increase our blood pressure, and then hopefully we return back to homeostasis and these things can be turned off. These slides here go over hormones that help to regulate blood pressure. So we talked about norepinephrine and epinephrine. These increase our heart rate and contractility, which would increase our blood pressure. Angiotensin II, ADH, norepinephrine, and epinephrine would cause vasoconstriction, which would also increase our blood pressure. ANP, atrial natriuretic peptide, epinephrine, and nitric oxide would increase vasodilation, and this would decrease our blood pressure when we need to kind of return back to normal, okay, or if it's just too high in general. Aldosterone and ADH, this would increase our blood volume and therefore increase our blood pressure, and ANP would decrease our blood volume, which would decrease our blood pressure. Autoregulation, this is how tissue can adjust its own blood flow to match how much demand it has metabolically, so how active that tissue is in a given time. Okay, so there's different physical and chemical stimuli that can lead to autoregulation. So I just wanted to mention that autoregulation is possible. Okay, you don't need to know any details about kind of how this works. We're not going to get into that in this class. Okay, pulse points, so we can check our circulation, make sure blood is pumping through these pulse points. Okay, so we have these different arteries where you can check. Commonly, it's checked through this radial artery here, right below where the thumb is in the wrist, and in the common carotid artery in the neck. We can also check it through the facial artery, superior temporal artery, brachial artery. This is how the blood pressure cuff tests your blood pressure. Femoral artery, popliteal behind the knee, and dorsal artery, dorsalis pedis artery. Okay, so this is showing how we measure blood pressure. So we have systolic and diastolic blood pressure. So when taking blood pressure, first you cut off the circulation of the brachial artery with the blood pressure cuff. Then you slowly release the pressure as you listen to the brachial artery with the stethoscope. So first you don't hear anything. As that pressure is being released, the first sound that you hear, you record what the pressure is on the blood pressure cuff at that moment. That's your systolic pressure. So that's the first sound heard. So that's when you can hear the blood pushing through the artery again. Okay, so it really has to push through the artery as the diameter is much, much smaller than it normally is. Okay. Then you keep listening and you keep hearing it push through, push through, push through. The last sound you hear, that's when you record the diastolic blood pressure. So now blood is flowing freely. It doesn't have to push through that artery anymore. Okay, so this is how you take blood pressure and check circulation. Okay, shock. So shock, the body goes into shock when there's an inadequate cardiac output. Okay. And this happens because of a failure of the cardiovascular system to meet the demands of the cells in the body. Okay. So the cell membranes are not going to function properly, cell metabolism is not normal, and cell death can occur when going into shock. Okay, so we're going to talk about these 3 types of shock. Hypovolemic shock, this happens when you have a large loss of blood. Vascular shock, this happens from extreme dilation of the blood vessels, okay, and decreased peripheral resistance. And cardiogenic shock, cardio, so this is where the heart cannot sustain circulation due to some issue with the heart. So when we're in shock, the RAA system is going to be activated. ADH is going to be secreted. The sympathetic division of the ANS is going to be activated, so our fight or flight response, which tries to increase our heart rate, right, to get our oxygen to our tissues. That's going to be important, right? And then local vasodilators are going to be sent out as well. Okay, so here's all that happens when we have hypovolemic shock. Okay, so when we have a decrease in blood volume and blood pressure, the baroreceptors in the kidney will increase secretion of renin. This acts on the liver and lungs to get angiotensin II into the blood. Okay, this acts on the adrenal cortex to release aldosterone, which acts on the kidneys, blood vessels, and heart. So kidneys will conserve salt and water to increase our blood volume and therefore increase our blood pressure. The blood vessels will constrict to increase the vascular resistance and increase blood pressure. Then we have our baroreceptors in the carotid sinus and arch of the aorta in the heart. These, when we see a decrease in the nerve impulses here, the hypothalamus and posterior pituitary will release ADH, which does the same 2 things in the kidneys and blood vessels as aldosterone. Okay, and the cardiovascular center in the medulla will increase sympathetic stimulation and increase release of hormones from the adrenal medulla, so the inside of the adrenal gland. And these will have the same effect on blood vessels, vasoconstriction, and they will also affect the heart to increase heart rate and contractility, which would increase blood pressure. Okay, and then once our blood volume and blood pressure go back to normal, we're back to our normal self, and we could turn all of these things off. Okay, so here are some signs and symptoms of shock. So you get clammy, cool, and pale skin, tachycardia, which is an abnormal heartbeat, weak, rapid pulse. Okay, so your body is trying to make up for that blood loss, but it's weak because it doesn't have enough blood if there was like a bleed. Sweating, hypotension, so low blood pressure. Altered mental status, so you can become confused. Decreased urinary output, thirst, and acidosis.